Hello, welcome to Picture Me Coding with Eric Aker and Mike Mull. Good morning, Mike.
Hey there.
How you doing today?
I'm doing all right. How are you?
It's 40-something degrees outside. That's just not that many degrees for me.
Yeah, well, when you live here in San Diego, you have to put up with some brutal winter weather from time to time.
Brutal is the word I would use. You know how we had the type theorist Nathan Mull on the show a few weeks ago?
I do recall that, yes.
Nathan talked about this album called Understory by a saxophonist named Ben Wendell, and I went off and listened to that record over and over and over again. Turned out to be really good. And the one you mentioned last week by Jeff Parker called ETA Fortet, also very good. I just kind of fell into this hole of these jazz albums. And somebody recommending a jazz album to me and the likelihood of me actually going off and listening to it and enjoying it, contemporary jazz album, is like not very high. It's like if you said, "Hey, I found this new TV show and it's a Western, you're going to love it." And I'm like, yeah, 1 out of 10 chance I'm going to love that.
It's probably got Kevin Costner in it.
I have never seen that show. So I followed more of the Ben Wendell track, and I discovered that he had an album called The Seasons that I also liked. The Seasons has 12 tracks, each named for 1 month of the year. So not a really wildly creative naming scheme for the songs on the album. You got January and then February. But I like this one. It's a little more ethereal and out there. I kind of describe it like saxophone whale sounds. And if I were a musician who played jazz saxophone and somebody said, "Oh, your album sounds like saxophone whale sounds," I would think to myself, this person's terrible. They hate my music. I don't ever want to talk to this person again. But honestly, that's how it sounds to me. And I really like saxophone whale sounds.
Yeah, well, you're an ocean person, so it follows that you would like whale sounds.
Maybe that's what it is. I'm out there with the humpbacks. What have you been listening to this week, Mike?
I'm still in the process of kind of reviewing stuff that came out in 2024 because, it's January and people don't release a lot of albums at the beginning of the year. But so anyway, I've been listening a lot to this album that's come up on various people's lists by an artist named Dochi. And the album is called Alligator Bites Never Heal.
Dochi. I'm going to guess genre is cumbia. That's my guess for the genre.
No, that's pretty far off. She's a rapper. So it's a hip hop album in a sort of a variety of styles, kind of old school, I guess. Parts on here that reminds me of stuff from the early 2000s, maybe. Kind of interesting and smart and funny, and sometimes it sort of veers into more R&B territory, but yeah, kind of a fun album. I had seen this album earlier in the year, but didn't really listen to it. And then she kept coming up on like my YouTube feed, and Mike Patterson Patterson Hood of Drive-By Trucker fame listed her on his end of year list of favorites. So I gave it a listen.
So you're taking hip hop recommendations from the Drive-By Truckers.
Yeah. I think
no judgments.
I think
no judgments. I just wanted to clarify at this point. That's all I wanted there.
Yeah, a little bit of a Southern thing, I think, going on. A little bit of solidarity, but it's fun. It's not all great, but there's several songs in here that I really like and have added to my 2024 favorites list. So
you told me the name of the record. It's got a funny name, the record.
Alligator Bites Never Heal.
Kind of like the Komodo dragon, right? Bites a thing, it gets a bacterial infection, chases it down, and then chomps it up.
I'm guessing that's probably the same idea, yeah.
We don't know for sure if that's how it works. Listeners, if you would like to reach us, you can email us at podcast@picturemecoding.com. We are also on Blue Sky. There is a Picture Me Coding account on Blue Sky. And recently we have started a Patreon. We have a membership level of $4 a month. If you'd like to support the show, we would love your support. We will thank you on the show. We'll read your name aloud, and we'll use your donation to support producing the show and editing it. That's available on Picture Me Coding, patreon.com, Picture Me Coding. So, Mike, you remember last week we were talking about the CAP conjecture? We were talking about Pod C, the Principles of Distributed Computing conference in the year 2000.
Rings a bell. Could you remind me, recap, no pun intended, what we talked about?
There's a conference called the ACM Symposium on the Principles of Distributed Computing, and they've been meeting for many, many years. I think it started late 70s, early 80s. And a number of the people whose papers we've read have presented at this conference, and they've been given awards at this conference. And I wanted to zero in on the year 2000, where distributed systems researchers gathered in the lovely city of Portland, Oregon, to pick blueberries and go to the Pod C conference. Leslie Lamport was given an award for his clocks paper, which is one of my faves. He gave a tutorial on TLA Plus, and most notably for our show last week, Eric Brewer presented his what became called the CAP conjecture and eventually the CAP theorem.
And CAP stands for consistency, availability, partition tolerance, or something like that, correct?
Yeah, partition tolerance, so clearly laid out for us. So we talked about CAP, and then we talked about FLP. We went back to 1985. We talked about Nancy Lynch's work. Lynch was one of the people, Fisher, Lynch, and Patterson, who worked on this FLP proof. FLP was about async systems, distributed systems that are async, and you couldn't guarantee a certain level of consistency that terminated in an async system, even if you have just one failing process. A very surprising result.
So you cannot reach consensus with one faulty processor, right? That's the kind of the crux of it.
Yes, termination, validity, and agreement. Those are the rules of consensus. Yep. So your description of FLP made a lot of sense to me. And I ended up kind of thinking of it in terms of Lamport diagram. You know, as Lamport diagrams, you've got these like vertical lines and they represent processors or maybe nodes or services, whatever you want to think in a distributed system. You've got some different things that are distinct from each other, separated geographically, and every vertical line represents one of them. And they send messages, and these vertical lines, you have these kind of arrow lines coming off of the vertical lines and bouncing off the other ones. As they send these messages, there's really no guarantee when they'll arrive. And when the response comes, if a response comes, there's no guarantee when that'll arrive. And you can kind of like build Lamport diagrams to show where things fall apart in practice. And your description of FLP kind of made sense to me. And ultimately, I ended up thinking over the last week, like, wow, really what Mike was saying is there exists a Lamport diagram you can draw where if you have one of these faulty processes, then you cannot achieve consensus. And so it wasn't like, oh, this is never going to happen. It was more like, you can't guarantee that it will always happen. It's impossible to guarantee that you can get around these restrictions. So FLP, pretty interesting result.
It is, but I'm waiting for the shoe to drop where you tell me how that relates to the CAP theorem.
So it does relate because we have the CAP conjecture offered in 2000. And if you remember when Eric Brewer gave his talk about CAP, in his abstract, he wrote, these are not yet, and yet was in parentheses, these are not yet provable principles, but merely ways to think about the issues that simplify design and practice. And I listened to an interview with Eric Brewer, and he said, yeah, I dreamed this up, and I kind of in my head sketched out kind of what a proof would look like, and I thought this should be provable. And then this is sort of, I'm paraphrasing what he said. He went off and talked about it. Well, Nancy Lynch, she proved it. She proved it with a person named Gilbert. I should grab their first name, but she sees Brewer's conjecture, the CAP conjecture, and she says, wow, this seems similar to FLP. It may be like a special application of the FLP result from 1985. So she and Gilbert, they prove the conjecture, and that's how it becomes the CAP theorem. Now, this happened in a paper that was published in 2002. So we were at Pod C 2000, Portland, Oregon, with the blueberries and Lamport and the cap talk that Brewer gives. And 2 years later, Nancy Lynch publishes this paper where she's like, yes, actually, you can prove that this is true. And this graduates it into a theorem from a conjecture.
It's
The paper's not very long, about 13 pages long. Go ahead.
it's Seth Gilbert.
Seth Gilbert. Oh, thank you for correcting me on
Both
that.
of them at the time, I think, were at MIT. So
The name of the paper is Brewer's Conjecture and the Feasibility of Consistent, Available, Partition-Tolerant Web Services. So it's about 13 pages. It is readable. The proof inside is one of those things that I read it and I go, yes, this makes sense. No, I don't get it at all. It doesn't make any sense. And then I go, yes, it makes sense. And then I kind of vibrate back and forth across this axis of I get it, I don't get it.
I have a similar reaction, which is sort of like, oh, yes, I follow your argument. It's very clear. Did you actually prove the thing that you said you're going to prove?
All right. I want to talk about their proof of CAP. And then today, I want to continue the CAP story and talk about like the legacy of CAP. That's ultimately what I want to get to. Have people heard of this thing? Why have they heard of it? Why did it have the effect that it did in our industry? I want to get to that question. But first, I want to talk about the proof a little bit. So Gilbert and Lynch describe the model that they're going to use for their proof. They talk first about consistency. And this quote, I want to give it to you, and I want to know what your take is on this quote. They write, atomic or linearizable consistency is the condition expected by most web services today. There must exist a total order on all operations such that each operation looks like it completed in a single instant. What do you think about that sentence?
It is somewhere between confusing and impenetrable.
I don't think it's that bad.
I think you have to have. It's one of those things where if you already know what she's talking about, it makes perfect sense, and if you don't, it seems confusing.
Well, first of all, she equates atomic and linearizable. So she's saying atomic or linearizable consistency. Sounds like these are equated. Linearizable implies total ordering. And the way they use the word atomic in the paper, it's like, it's as if it happened in an instant. So we can kind of set up examples in our head. Let's imagine we've got a basic database where we can write instructions and we can read instructions. That's it. You can't delete, you can't update. You could just write a thing or you can read a thing. That's it. That's all you can do. And we now have maybe multiple nodes participating in running or operating this database. So I don't want it to go down. I'm running on a Kubernetes. You're not supposed to run databases on Kubernetes. We're going to run this thing on Kubernetes. And in Kubernetes, a node can be arbitrarily taken offline just because we need to update it. So I got to run multiple. Now, an atomic transaction means it happens, and then when the next one happened, the first one is like completely resolved. It's completely settled. It happens in an instant in time. So there's a total order, almost like natural order that we would think of on a clock. And I think that's what's going on with linearizable. Does that sound right to you?
Yeah, I think the idea of total order, I think, is important here. It's one of those things that comes up a lot in computer science, and I think the sort of key idea here is that everything that happens can always be put in terms of this happened before that or this happened after that. There's no sense of these two things are potentially happening at the same time.
Right.
Which would require a partial order. I guess I've tried reading the linearizability paper by Jeanette Wing and forget the other author, but it's hard. It's hard to understand. But I guess I've kind of boiled it down to in my head to you want basically the same thing that would happen in sequence if you were on a single node and you didn't have multiple processes running.
Yeah, it's easiest for users to understand this kind of model, because it's like I can pretend there's one instance. I send all my requests into this magical system. It doesn't matter if there's one or many. It operates in the same way. It just sort of orders every single request I send in. And the total order means every single request can be put in an ordering with respect to every other request, right? They all just sort of go together at their moment in which they happened, their single instant. What do you think about this? Linearizable or atomic consistency is a condition, here's my emphasis here, expected by most web services today. What do you think about that part?
I think that is probably a little bit too restrictive. I don't think people really expect that. And I think people, do to some extent tolerate conditions where that does not happen.
If they don't expect that, what do you think they expect?
Well, I think, they expect that like if you do a request and you get a value and then you do another request, you'll get the same value if somebody didn't change it. Uh, I think people expect that things will at some point in the not too distant future be consistent with reality.
What if we're both doing bank account transactions? You are doing something with your bank account, I'm doing something with my bank account. A total order would imply that what I'm doing with my bank account has some ordering with respect to what you're doing with your bank account, right? Like you're withdrawing 40 bucks, I'm depositing $100. Do you think that most users of web services have the expectation that these are linearizable?
I think people, well, with bank transactions in particular, I think people do have the expectation that the order in which they physically perform transactions will correspond to the way that they happen on the web service. You know,
Maybe I gave too weird of an example there by saying these are completely unrelated. I was thinking about a database, right? If I withdraw $40 and then I send a payment to somebody else and I don't have enough money in my account, I think we would expect that to be linearizable, right? Like I withdrew, I am now less than a certain amount. I want to send out a payment, there's not enough. The bank can just figure that out. I have some doubts that users expect linearizability, but I'm kind of getting too deep here. So, their model is consistent, atomic, or linearizable. That's very important. It is available, means all requests receive a response, but there's a footnote. They don't put it as a footnote, but there's a detail. All requests receive a response, but we haven't said how long it takes for the response to show up. And finally, partition tolerance. That means messages can be lost. Partition tolerance, almost like all messages are lost from a node that got cut off in the network. Consistency would be even though some messages may not get delivered, we want it to be consistent, or availability means we respond to all requests, even though some messages may get lost. So, the mathematical impossibility that they demonstrate in this paper is this. It's a proof by contradiction, very similar to FLP, where it's possible to construct a series of events which show that our guarantee of all three properties, consistency, availability, and partition tolerance, is violated. So, to restate that, you can build like a Lamport diagram where you say this happens, if the timing or delivery of these messages looks like this, you can't guarantee all properties. So here's an example. They say, well, this is a little easier to demonstrate with message loss. You just have two nodes and they happen to be cut off from each other. There's a network partition. They can't talk to each other, but they're two nodes. We send requests into the system. One of those nodes receives a write request. The other one receives a read request. Well, it's kind of obvious and trivial to say, if they can't talk to each other, they both will respond to the requests they get. They're available. The one that receives the read request will respond. It has no clue that that other one got a write, right?
yeah,
So we can't promise that they will be consistent. What do you think? Does this proof make sense to you?
yeah. And by saying we can't promise they'll be consistent, what they say there is that if there's a write to node A and that doesn't get communicated to node B, then when I read node B, it's not going to have the latest update that happened on node A. So therefore, the results, a request to node B is going to give me a different result than a request to node A. So therefore, we are not consistent. So they start the proof by saying, let's assume that we do have consistency, availability, and partition tolerance. And then they proceed to show in this particular instance that on that assumption, they do not, in fact, have consistency. So they have a contradiction. And so their initial assumption has to be wrong.
Now, I've heard this described, cap theorem proof here, I've heard it described as like an extension of FLP. So it is kind of interesting that Nancy Lynch is like, I thought I was out and you dragged me back into the impossibility game.
This one feels a slight bit different to me than FLP. I mean, it's very similar in the sense that it's a proof by contradiction, and they're starting with a similar model in the sense that it's an asynchronous network.
Mm-hmm.
But I think the one difference here is that the situation they describe it could in fact occur. It's fairly plausible, whereas the result in or the sequence of events they describe in FLP is somewhat contrived, maybe.
Contrived. Ooh, fighting words there, Mike.
Well, yeah, I mean it's an improbable sequence of events, maybe.
It's improbable, but the fact that it could happen means that you can't guarantee the result.
Right.
So they start with, okay, what if there's a network partition, what's happened? But then they extend it in a surprising way. This is their corollary 1.1. And this is where it gets a little harder for me, and I think I'm gonna need to rely on your help. They say, okay, what if we guarantee no messages are lost in the system? Which, first of all, sounds like a pretty surprising guarantee. And then immediately after that, they say, well, an async algorithm doesn't have any way to know if the messages have actually been delivered or if they're just going really slowly. So no messages lost is kind of equivalent to saying all messages are lost. Is it?
Yeah, so I think in Theorem 1 here, where they essentially prove the cap theorem, they're imagining a scenario where none of the messages arrive.
Mm-hmm.
They explicitly say the messages are lost. And in the corollary, they're saying, well, they might just be delayed indefinitely.
Mm-hmm.
And so since we don't know when they're going to arrive, there is a possibility of a situation that is indistinguishable from them not being sent at all.
Mm-hmm.
But you can end up with this. You can have this situation where the messages don't get sent. Somebody does a read. The read demonstrates inconsistency,
mm-hmm.
and then at some time later in the future, the messages do arrive.
Right, because they were just slow. Right,
they were just slow. But from the standpoint of somebody using the system, it doesn't. It's is up until that point indistinguishable from the messages being lost entirely.
I think that's a very good description. And for me to understand this goes back to how they use that word at the very beginning when they talk about atomic or linearizable consistency. It's as if things are happening in a single instant. We can't have what they would think of as like an atomic execution. I send a write message into node A, or it just happens to land on node A, the first node, and it doesn't instantaneously get communicated around to every other node. In this case, there's just another node, node B. And at some point, that message has to go from A to B, even if I'm responsible for sending it to every single one. I can't guarantee how long it will take my messages to land on both of those. And so because there's like a physical restriction here, right? My messages have to go, they have to communicate, they have to go over a wire, they have to travel a distance. And that alone means I can't guarantee instantaneous agreement. And so if I want agreement, I need to sacrifice availability. Like if we put our software engineering hats on and we just try to naively solve this without thinking about other stuff that we know, like how do we solve it? If you say, well, I send a message in and I want to make sure before anybody responds, any other nodes respond, that they know the state of the latest messaging. I mean, how would you solve that problem as a software engineer? You've got the ticket now, Mike.
I just deal with the distributed system entirely and just get one big computer running one process.
Have you sacrificed any of the letters from CAP when you've done that, you think?
Well, I think I'm sacrificing the P by just basically eliminating the possibility of network partitioning.
I like the P. My favorites are P and C, I think.
This is probably the most difficult part for me in these proofs is the idea of partition tolerance or tolerance of network partitioning is, I think I'm stuck on the word tolerance because, for instance, in in the setup of the theorem one here, they basically say, well, we're assuming we have a system which provides all three. And then we're also saying that none of the messages are delivered between nodes. So the way that we're achieving network tolerance is we have two completely separate nodes that can't communicate. Therefore, we are partition tolerant. And yeah.
So, but is that partition tolerant because you send a message, it may hit either one, and they can still talk to you?
Yeah, so both nodes are available, so they do have availability, but they've also demonstrated that they cannot provide consistency. And that anyway, I trip on the word tolerant because tolerance implies to me that, okay, the communication between my two nodes are down, but I'm still going to provide you with good results. And really all they're providing me with is results.
Yeah, that goes back to consensus, right? Termination, validity, and agreement. There's nothing, it's invalid, and there's not really an effort at agreement. Really, what you got there is termination.
Yeah.
Maybe the ticket as you go to write your code and submit a PR is like, oh, if the network is down, we'll just return this constant value. That's good enough, right?
Right. Well, we've talked a little bit about this, and it's like you have worked with Raft and studied Paxos and stuff like that, and those systems claim to provide. Claim to be CP systems, meaning they are consistent and also partition tolerant. But my interpretation of the way they are tolerant is that if one of the nodes is not providing a consistent response, they just don't allow requests to it anymore. Therefore, it's no longer available.
I actually, that's not the first thing that leaps to mind. I don't know if that's how I would define it for the system. The way I would define it for like Raft would be if a node drops out, when it comes back and re-enters the cluster, it can be brought back up to date in a consistent way, but it won't be available until it is.
Okay, I'll buy that. It seems like a subtle distinction between my interpretation, but you've done Raft and I have not. So
maybe what we can say for our own benefits and for the benefits of our listeners is we're not quite comfortable with the phrase partition tolerance.
Yes.
Can we just say that the network sucked for a bit?
I would like clarity on this, although I do think that thinking about this stuff has sort of clarified to me, the issues that they're trying to address with the cap conjecture and the cap theorem.
I think I've gotten a little bit more clarity around it too. I thought that I understood it, and then I started reading, and I started to feel like, wow, maybe I don't understand this the way that I thought I did. I was saying last week that it's fascinating to me that FLP and the cap theorem, they're interested in mathematical impossibilities. It's like there's some sort of hard limit to information. You mentioned MP complete, makes me think of the halting problem, Gödel's incompleteness, or even like maybe this is a little dramatic, but even like the speed of light in physics. There is a limit here. We're not going to break this particular barrier. There's this funny comment from a paper that I mentioned last week, the 100 Impossibility Proofs paper from 1989 by Nancy Lynch. She says, this is a quote, "Impossibility proofs are much easier in our area than in most others. This is because the limitation of local knowledge is a fundamental fact about the setting in which we work, and it is a very powerful limitation." I meant this joke to you, but it's like she's like in Good Will Hunting. It's like, this is easy for me, okay?
Yeah. It reminds me of this anecdote about, I can't remember the mathematician's name, but he comes to class late and he sees this problem on the board and he thinks it's homework. So he goes home and he solves it, and it turns out it's a famous unsolved problem. Anyway.
Yeah. She talks about local knowledge, which actually shows up in a paper from 1984 called Common Knowledge. That paper, I'm still working my way through. But local knowledge is like knowledge confined to the node. And so that's the only thing you have to work with when you're thinking about these systems. If I've got node 1 and node 2, node 1 has local knowledge of node 1. It cannot know what node 2 knows. It can only take action based on messages it receives or other events that happen. Nancy Lynch writes in that impossibility proofs paper, it's probably true that most system developers, even when confronted with the proved impossibility of what they're trying to do, will still keep trying to do it. This does not necessarily mean that they are obstinate, but rather that they have some flexibility in their goals. For example, if they can't accomplish something absolutely, maybe they can settle for a solution that works with, quote, sufficient high probability. In such a case, the effect of the impossibility result might be to make a systems developer clarify his or her claims about what the system accomplishes. Huh. She's saying here we offer we offer these impossibility proofs. It doesn't just sort of tell you to stop doing the stuff, but often developers want to keep building their systems, and these impossibility results force them to clarify their claims. And that's, I think, the real moral of the story with the CAP theorem. It becomes a thing that people know about, it becomes a thing that people talk about, and it becomes a thing that people have to kind of address. If they produce a database system, they often feel compelled to say, here's how this fits into the CAP theorem. Does that sound right to you? I mean, I feel like the CAP theorem mentioned all over the place. And maybe that's just my own weird little lens.
Yeah, I think maybe even Brewer, you told me this, but I think Brewer even claimed that, thinking along these lines is kind of what led to the NoSQL revolution.
Mm-hmm.
People had been stuck on sort of the ACID model of transactional isolation for so long. And then when this result came out, people started thinking about, well, what if we didn't have to worry about, such hardcore consistency or
Mm-hmm.
isolation of transactions? What if we let that slide a little bit, and what would we end up with? And
Yeah. What if we tried to make an AP system? What would that look like? I feel like CAP theorem is everywhere. I feel like there's like a virality to it. Do you think? I mean, I did this poll at work, just like how many and people I work with, they're great developers. I have a great team, wonderful group of people. And I said, how many of you, just a poll, how many of you have heard of the CAP theorem? And there were only 8 responses, so not a big team, but only 8 responses. And it was completely split down the middle. 4 had heard of it, 4 hadn't. And the people who had heard of it were like, don't ask me to describe it. I've heard of it.
yeah, it's got this sort of this sounds pejorative, but it's not meant to. It's got this kind of like Hacker News vibe to it, where it's kind of like, I'm going to post something about this to show you how clever I am. But so I have a couple of theories on why this became such a common thing. One is that I think it's useful as a marketing tool. So, like in the NoSQL world, people started talking about eventual consistency,
Mm-hmm.
and eventual consistency became sort of a buzz phrase too. And I think the reason why it did is because saying that we are eventually consistent sounds better than saying our database is not consistent.
We make no guarantees about consistency, okay? You could send it right in, and I might lose your stuff, like MongoDB when they first started. I have no guarantee, but you know what? We'll go pretty fast.
Yeah.
I might lose your data a lot faster than any other database on the planet.
Yeah, so I think it has, the CAP theorem has this thing where you can sort of use your approach. The thing that you leave out is sort of your selling point. We're not consistent, but reads are super fast, or you can do writes with very low latency because you don't have to wait around for everything to sync up. So that's one theory I have, is that it just sort of became a useful marketing tool for people selling databases.
I want to hear your other theory, but I want to give you mine first.
Okay, lay it on me.
Then I want you to weigh mine, and then I want to hear your other theory. So one is marketing from you. Here's my theory. I would propose, and it sounds like you're in agreement with my first statement, which is that a lot of people in our field have heard of this, whether they're interested in computer science, distributed systems theory at all. That if you were going to go interview for a job and you're going to deal with distributed systems at all, it'd be like table stakes to have heard of the CAP theorem, that it's extremely common thing for people to reference. You're kind of on board with that? You think that's true?
Absolutely, yeah.
Okay, so here's my theory. The CAP theorem is a really cute, convenient taxonomy. It's either CA or CP or AP, and we love that shit. We love the nice, clean buckets, right? You give me a database and I'm going to paint it with the colors red, yellow, or blue. And it will permanently have that color. And then in my head, when I have that data, when I have a problem that is a red problem, I will know it's one of these things. It's this convenient categorization that feels extremely empowering. We know with distributed systems that tons of stuff can go wrong. There's so many errors of assumptions and knowledge that I can have. There's so many mistakes I can make. But you're giving me a tool that I can immediately categorize I could just put a stamp on its forehead, CP, and know how to use it. Well, that's quite an attractive idea to me. So my argument is we love taxonomies, and this is a very convenient taxonomy, and that's why it became so popular to talk about.
Yeah, I think there's something to that. I think it sort of intersects a little bit with the marketing idea.
Did I stump on your second? What's your second theory?
So my second theory is that the reason this has such a cachet in the tech world is because of the word theorem. So people talk about the FLP result sometimes, or they talk about, you might talk about some language being Turing complete or something like that. But the word theorem in here, I think, gives it a little bit of a mathy feel.
It's like saying we went to court, there was a decision, it was decided. Boom.
Well, like
canon.
In the social sciences, they always talk about like physics envy, so people in certain fields, they feel like it gives their field more legitimacy if they can throw a partial differential equation into their paper. And I think there's a little bit of that in here, where, especially like in the interviewing scenario, where you can, you should know this because it's a theorem. This is not just an idea. This is a theorem. And
maybe you started off with this theory, and I was like, I don't think I buy this. But then you kept going, and I was like, yeah, maybe you're right, actually. We never really ask our listeners to reach out. This is one on specifically I would want to know. If you're listening to our show, have you heard of the CAP theorem? Listeners, I'm honestly asking, have you ever heard of the CAP theorem? If you have heard of it, why do you think it's a thing that people have heard of generally? I would be super interested to read what people think. Send us an email, podcast@picturemecoding.com, or just post on Blue Sky. I have heard of CAP theorem. This is why I think it's so widely talked about. I want to know what reasons people would give for this.
However, we should probably move on to chapter 4.
Yeah, chapter 4 is where I want to get to next. So CAP theorem, commonly talked about. It's common to talk about, Raft. Oh, that's consistency with partition tolerance. DynamoDB or Cassandra. Those are available, eventually consistent, but available and partition tolerant, right? PostgreSQL. Oh, wait a minute. That's a trick question. Google famously has this Spanner blog post where they're like, we're pretty much all CAP all the time. Come at me, bro. That's kind of what they say. They're like, okay, fine. There's a purist answer, which is no, partitions can happen. During a partition, Spanner will choose C, forfeit A, so it's technically CP.
Yeah.
But in practice, we find that Spanner does meet this bar with more than 5 nines of availability.
Yeah, so I think this goes back to Lynch's point, which is, just because it's impossible doesn't mean you can't do it arbitrarily well if you're willing to invest a lot of effort into it.
Well, here's what I want to get to for chapter 4. The legacy of CAP theorem. It became so widely discussed that you have people like Martin Kleppmann in 2015 writing an article called "Please Stop Calling Databases CP or AP." He's probably bummed that we're having this episode about the CAP theorem, because you read this post from him and he's like shaking his head. Now, Kleppmann's a CS professor. If you haven't heard of him, he's the author of Designing Data-Intensive Applications. We talked about that book many episodes ago. It's a great book. Wonderful book.
Yeah, definitely. One of the better technical books in the field.
And last week, you raised one of the points that Kleppmann raises here, which we'll get to in a second, but Kleppmann says if you want to refer to CAP as a theorem, using the gavel of the mathematicians, bang, theorem, as opposed to a hand-wavy concept in your database's marketing materials, you have to be precise. This is from Kleppmann's article. He writes, mathematics requires precision. The proof only holds if you use the words with the same meaning as they are used in the proof. And the proof uses very particular definitions. And he says it's a highly specific model that they start with. It's not just any old system. He writes the CAP system model is a single read-write register. That's all. And what it says, it doesn't say anything about transactions that touch multiple objects. They're out of scope. So did you get this feeling when you look at the Brewer talk abstract? He's like, in practice, we find that you have to really pursue optimizing around certain things. You look at what Brewer, what happened in the 90s. They started building a database at Inktomi where they're like, yeah, we want it to be available to like a CDN or like DNS. And we'll sacrifice immediate consistency. We'll try to solve that later. We'll try to pick that up over time. And he went to these database conferences, and database people were like, that's not a real database. And he was like, it is, right? And then he started talking about this breakdown of CAP. And then you look at the Gilbert Lynch paper, and they're like, yes, atomic linearizability and availability and partition tolerance. Did you have, like, you go from what Brewer was saying in 2000 to the paper in 2002? Are they really on the same level there? I guess the question is Brewer talking about atomic linearizable consistency in 2000?
Well, I mean, there's clearly some differences, and I think, Brewer, I believe, was trying to be somewhat more informal about it. He was talking about his real world experiences building real systems. And I think when they went to the point of trying to prove it, they, of necessity, had to go to this more formal and kind of constrained model to make it provable. I buy Kleppmann's argument here that what they prove is a very specific thing, and that if you don't follow the details of what they actually proved, it's slightly less of a valid thing. But I do think it's still a useful way to think about distributed systems.
Oh, you got to save that comment for the end. We're going to trash it now. At the end, you have to come in and say, it's still useful. Okay. So one thing I loved in the Kleppmann piece when I read it, I always had this discomfort with this phrase, partition tolerance. And in my head, I was like, there's something wrong with the network. What is partition tolerance? The distributed systems literature talks about network partitions, but it's like it's so much easier as a developer to just talk about straight up failures. FLP is like failure, right? The node just stops processing. That's easier to understand than partition tolerance. The thing crashes. That's not a partition tolerance, but I guess it kind of can be, right? Kleppmann writes, partition tolerance, and in parentheses, he puts terribly misnamed, basically means that you're communicating over an asynchronous network that may delay or drop messages. The internet and all data centers have this property. So you don't really have any choice in this matter. So back to your question, Mike, he says, partition tolerance means, are you using the internet?
Yeah. To be perfectly honest, I'm not super comfortable with his definition of it either. I think there's a couple of things that throw me off with this idea. One is that there is a concept of partitioning databases, which has absolutely nothing to do with this concept.
Okay, all right.
So,
completely different idea, same word, overloaded word.
Yeah, so you can partition a database on some, key so that you're keeping data of, like, say you have a huge data set and you don't want to put it all on one storage system. You could partition it, let's say, by some key, or maybe like the zip code of the user or something like that. So you can.
Oh, that was the exact example I was thinking. You've got 400 million people in the United States. You want to put them all in your database, but it's a lot of rows.
Right.
So you can chunk it up into sub databases that are partitioned by some specific column. And you gave the example which I would have given. Maybe their zip code.
And so this is a slightly different idea here. The other problem is that there is a concept in networking called partitioning, where you intentionally create subnetworks that can't communicate with each other. So, that's much closer to the idea that I think is trying to be conveyed here.
Mm.
But I think the thing that trips me up is that you have this deliberate thing called partitioning where you're trying to keep nodes from talking to each other. And then you have this idea that they're talking about here, which is kind of like partitioning happens because something went wrong and the nodes cannot communicate anymore.
The IT department messed up their network and firewall rules. Fix them. Submit that ticket. Well, I mean, Klipman says the only fault considered by the CAP theorem is a network partition. That is, nodes remain up, but the network between some of them is not working. That kind of fault absolutely does happen, but it's not the only kind of thing that go wrong. Nodes can crash or be rebooted. You can run out of disk space. You can hit a bug in the software. Personally, Mike, these are the kind of failures I'm a lot more interested in because they're my fault. If it's a network problem, it's like, hey, somebody go fix the network, okay? In building distributed systems, Klepman continues, you need to consider a much wider range of trade-offs, and focusing too much on the CAP theorem leads to ignoring other important issues. So network partitions, terribly not so useful, misnamed idea for us to bat around.
Yeah, this is definitely the part of the CAP theorem that confuses me the most. And I think his point is well taken, but also both here and in other places, people have made the point that this is not really that much of an option anymore because almost all the systems we're talking about are communicating over, networks that will probably display this behavior unless you're on maybe a really reliable internal LAN or something like that.
That's the interesting thing about our contemporary milieu. You have distributed systems whether you want them or not. It's kind of like bed bugs. All right, so partition tolerance, badly named, not even a property that we can get away from. He goes on to say, Klepman does, that consistency and availability, as given here in the CAP theorem, they're not very useful for what we normally want to talk about. He emphasizes a point that you raised last week, actually. Consistency in CAP means linearizability, which is a very specific and very strong notion of consistency. Sorry, I'm quoting from him now. In particular, it has got nothing to do with the C in acid, even though the C in acid also stands for consistency. You meant that point last week.
Yeah, to be fair, I probably got it from him, but
Oh, okay. No credit for you then.
he gives a nice example too of two people are talking on the phone and they're looking at a website that has the results of a soccer game, and one person on the phone says, "Hey, our team won," and the other person refreshes their browser and says, "According to my web browser, the game's still not over." And he illustrates how that could happen in a real system pretty easily if the right message that updates the server that the second user is seeing does not happen soon enough, he might get results that are out of date. In this particular case, because they're communicating over a back channel, he knows that what the results are supposed to be, and so they look inconsistent to him. And that is a case he uses that as an example of something that's has not been linearized.
Well, I was that dumb example I gave of you going to the bank and me going to the bank. I was trying to imply that who cares if those are linearized? I mean, I guess the bank probably cares because they may run out of money at that bank, but like our transactions have nothing to do with each other. And a lot of times when we use databases and web applications, we can actually isolate things, right? We say, here's a user, they want to submit an update to these rows in the database, these rows with these identifiers. Here's a completely other transaction that is interested in some completely other rows. We don't have to order these things. They have nothing to do with each other. So linearizability, there's no point, right?
Yeah, I mean, unless like I'm Venmoing you money and then you're using the money to pay a bill or something like that, then we probably need some coordination. But otherwise, you
I, I think that's why the bank is a good example, because you and I might have completely disjoint transactions, and I might myself have dependent transactions. There's a causal relationship that have to be put into an ordering. So that's consistency, Kleppman says. The CAP theorem talks about linearizability. And you got to ask yourself, is that really what I care about? Is that really what we want? Is that really what our databases are interested in or should be interested in? Kleppman also says availability in CAP is defined as, quote, every request received by a non-failing node in the system must result in a non-error response. It's not sufficient for some node to be able to handle the response. Any non-failing node needs to be able to handle it. Many so-called, quote, highly available systems do not actually meet this definition of availability. So he's saying even this concept of availability here is pretty strong. So consistency very strong, availability very strong. And he also says the CAP theorem, this is again a quote, says nothing about latency. How long does it take? Which people tend to care about more than availability. This is one of the problems I have with a lot of the distributed system stuff is they're like, let's say that we have no proof that the message ever arrives. So a message that goes arbitrarily slow is the same as one that never arrives. And I'm like, yeah, but I really want the messages to arrive, and I really want them to arrive within like 30 seconds. Okay, like that's important to me. Can we talk about those conditions, that model?
Yeah, there's a lot of stuff in distributed systems that seems to me to be time dependent, but I really want somebody who's more knowledgeable about this stuff to explain the discrepancies there.
Well, it goes back to Lamport, right? It's special relativity, Mike. That's the answer.
Yeah. Yeah, I mean, if I'm on a spaceship traveling at the speed of light, then all bets are off. But
Kleppman says CAP available systems are allowed to be arbitrarily slow to respond, and they can still be, quote, available. They can still be called available. Going out on a limb, he writes, I'd guess that your users wouldn't call a system, quote, available if it takes 2 minutes to load a page. And so Kleppman's arguing you're using the CAP theorem to judge databases in the real world, but the CAP theorem talks about things you're probably not that interested in. The consistency model that often appears in databases or in web systems would be serializability instead. And serializability is not total order. It's like you could sort of put things into an order. We want to ask this question. It's like a way of asking this question. It's like, exactly how consistent do you want your system to be? There's also read your writes. Like I could set in a request to change something. And if you keep track of the fact that I am sending in that write request, that when I send in a read, you could be like, oh, Eric came in to make a change. We sent his request over to node A. Now he's coming back to read. I'll send that over to node A too. And then boom, it's as if it's a single node. Well, that's not linearizable consistency across the whole thing. I'm reading my writes in that case. It's a different consensus model. Linearizability, on the other hand, it's like it's very strict. What I say make any sense at all?
yeah, I think so. I think linearizability is a tough idea to internalize. You know, there's an example in the Wing paper also where they describe this scenario where two writes could be happening concurrently in a technical sense, but it's possible that even though you haven't gotten a response back from one of the writes, the state of the thing is already as if the write had been completed. And so there's like an assumption that, you know, if two processes, if process B starts writing and then process A reads the value and it gets the value that B wrote, and then C does a write, subsequently, if something reads that value, it's not linearizable if it reads the value that C wrote. And again, this is one of those things that's hard to envision without a picture. But
maybe you should sing about it in a Lamport diagram song. Well, I think what I would say instead is like ACID. You made this point last week. ACID, the consistency and ACID is generally serializability, which is a different set of guarantees about consistency than linearizability. And I think one easy way to describe that too is you can have stuff happening where you're writing to the database. These things happen roughly at the same time, and you could sort of wall them off and be like, here's some writes and here's some other writes, and they don't need to relate to each other.
Yeah, I guess the bottom line is that linearizability is a criterion that's not met in a lot of real world systems. And
Yeah.
if you relax
Yeah.
that criterion, then the way the CAP theorem is proven is less valid.
Right, exactly, right? That's Klepman's point. It's an interesting point. If you're not interested in linearizability, he's ultimately saying, are you really interested in the CAP theorem? Are you really interested in seeing how the CAP theorem applies to this database where you're never going to try to exercise it to that degree? He says, this is a quote, if you want to provide linearizable semantics, he says, this is CAP consistency in your database. You need to make it appear as if there's only a single copy of the data, even though there may be multiple copies, replicas, caches. This is a fairly expensive guarantee to provide because it requires a lot of coordination. It's like every single write, you got to like lock the thing down and be like, okay, does everybody know what happened? Okay, cool. We could start having requests come back again.
Right. And then you're adding, almost certainly adding latency to the system to do that.
Yeah. Yeah. One of the fun parts about Klepman's post is he goes through and he's like, well, what about DynamoDB? What about PostgreSQL? What about, and he just starts like categorizing all these. How would you look at this? Because this is something people do. Like you'll see questions on Stack Overflow. Hey, I'm looking at Mongo. How does it fit into the CAP? Is it AP? And then people will argue about whether it's AP. And other people will reference the Klepman post and say, stop arguing about this. Not useful. Klepman says PostgreSQL provides serializability. Oracle provides neither serializability nor linearizability. It's like, what does it do? And then he ultimately says, this is my favorite line in his piece. This is a quote. The fact that we haven't been able to classify even one data store as unambiguously AP or CP should be telling us something. Those are simply not the right labels to describe systems.
Fair enough.
Guess I'll stop doing it then. He does a good. He tries to exhaustively. I mean, again, he knows his stuff. He wrote this book, Designing Data-Intensive Applications, where he talks about Cassandra, React, DynamoDB, PostgreSQL. He talks about these different things, and so he's saying you can't easily break them up. The taxonomy you thought you had with CPAP, it doesn't really apply. So you're not actually getting this easy categorization you thought you were getting. He has a reference to a paper called Highly Available Transactions, Virtues and Limitations. I was actually happy to discover this, rediscover Klepman's post, and then see this paper in there. If you've ever gone to Jepsen, Jepsen is well known in our field for validating whether or not databases remain consistent under load and failing scenarios. And so Jepsen publishes these tests. There's an Elasticsearch and a Redis and a PostgreSQL, whatever database. Jepsen will go out and they'll run their test suite on it. And in Jepsen, there is this tree or graph, actually, I think, of consensus models. And I always remember maybe 4 of them. There's like read your writes, and then there's linearizability and serializability, and then there's some of these are partially available, and some of these are fully available, and some of these are partially consistent, etc. He's got this color coding. Well, the person who writes that, Kyle Klingman, he took that tree of consistency models from this paper that Klefman references. Again, the paper is called Highly Available Transactions, Virtues and Limitations. And in that paper, this is what they write. Quote, despite its narrow scope, the CAP theorem is often misconstrued as a broad result regarding the ability to provide ACID database properties with high availability. This misunderstanding has led to substantial confusion regarding replica consistency, transactional isolation, and high availability. So now I put it to you, my friend. Are we confused? When you hear people talk about the CAP theorem, are they doing this? Is it CP or AP? Are they using, in your recollection, in your memory, when people refer to it and they seem to know the CAP theorem, are they applying it to PostgreSQL and Elasticsearch and Redis or whatever other data store?
I probably hear it more in the context of NoSQL type of databases than I do in relational databases. But yeah, I mean, I think people do try to analyze all of these systems through that lens. And I guess, as a follow on to that, what you can also pretty comfortably say is that despite what the limitations of the CAP theorem implies, people are still making databases. that work perfectly well in most cases.
Mm-hmm.
So
Mm-hmm. The point you made is true. In an interview with him, I heard Eric Brewer mention that the CAP theorem really helps inspire the NoSQL movement. It frees people up to prioritize non-ACID guarantees. It's a way of justifying and saying, look, we don't always have to provide an ACID database to provide something that's useful. And Brewer has this paper, the CAP theorem, 10 years later, 2011, I think, where he kind of describes how he says people misunderstand the spectrum of CAP and the trade-offs. This is a quote. He says, the binary part captures people's attention. They often don't talk about things like how to recover from partition tolerance. So even Brewer is like, you're getting a little too excited about, he calls it the binary part. What do you think he means by that?
good question. What do you think he means by it?
I guess I was guessing like the yes or no, but I don't know if maybe does he mean the APCP thing? Maybe that's what he means, the binary. Like Kleppman says, you're talking about databases that have multiple nodes, so that implies the P, the partition tolerance. You're using a network. You can't guarantee that all messages are going to get there, partition tolerant, okay? So then you get to choose availability or consistent. It's highly unlikely that you're going to build a database that lives on a single machine. Let's not talk about SQLite. Let's ignore SQLite. SQLite, for the purposes of this conversation, does not exist. So you probably have AP or CP. Well, that's a binary thing. And he's saying this is what captures people's attention. And I think that goes back to my suggestion earlier that it's nice to have a taxonomy. It's nice to have buckets. It's nice to have labels. It's nice to have a broad brush. Our industry is so confusing. You look at FLP and how do I actually apply FLP to my work? Mostly, I won't apply FLP to my work.
Yeah, I think there's probably, so as I said earlier, I still think CAP is a useful way to think about systems.
Well, that's perfect because that's the question I want to end with. Bring it home for us, Mike. Land the plane. Do we throw away CAP theorem is the final question I have for you. We told the story, 2000, Portland, blueberries. Proof comes 2 years later. 15 years later, you got Kleppman. What's useful about it still, though?
So I think if you try to think of distributed systems and you take every conceivable scenario into account, there just isn't a good language for it yet. So it's hard to compare two databases it's hard to compare two distributed systems on the whole universe of details of distributed systems. And so the CAP theorem gives you sort of a model on which to start with at the very least. I was educated as a chemist originally, and when you're learning chemistry, before you get into the details of real quantum mechanics, you learn this theory of what they call hybrid orbitals. So, it's kind of an idea that was invented by Linus Pauling, and it pertains mostly to the bonding of inorganic molecules, but it's kind of a slight simplification of quantum mechanics, but it gives you this framework where you can think about, why is benzene a flat ring, and why does this why does this particular bond not rotate like other bonds and things like that. And so I don't know. I think it's a leaky analogy here, but I think there's a certain aspect of the CAP theorem that's kind of like that too, where I can't think of everything about distributed systems that might come into play here, but this CAP theorem gives me sort of a framework where I can start. What are the things I'm trying to achieve? What are the properties that I want my distributed system to have? What are the trade-offs that I have to make to get the thing that's most important to me, knowing that I can't achieve all of the things that I want, that I would, conceivably want? What am I going to prioritize and what am I going to trade off?
That was beautiful.
Okay, we're done then.
It made me realize that CAP theorem, there's a kind of simplicity. I don't mean that in a pejorative way. There's a simplicity that it offers me as a model to think about what's possible and what's potentially improbable. I won't even say impossible because most of the time I don't want linearizability, right? And that simplicity then allows me to look at the trade-offs that you described. It's kind of like ordering a pizza. Can we do half and half? There's a lot of people in my house who don't want pineapple on the pizza. Pineapple in this case would be like serializability, and anchovies is linearizability. Most of the time you don't want that.
Have you thought about getting 2 pizzas?
Yeah, that is partition tolerance.
That's probably as good a definition I've heard of partition tolerance. Getting 2 pizzas.
Yeah, because you can't take a slice from one pizza and shove it into the other pizza and make it look like it really belongs. Like once you pull that slice out, it's not going to just fit cleanly into the other one. Those messages are lost between those pizzas, Mike.
There's a blog post in here somewhere about the CAP theorem as
pizzas.
As pizzas. But...
All right. Well, thanks for going on this journey with me. When we go on these journeys, Mike, I often start off going, oh, I know some stuff about this. And then I read and I go, oh, it turns out I know virtually nothing about this. And then we go a little farther and I go, oh, I feel like I'm getting it. And then at the end, I'm like, where the hell did I go? I just wandered through the woods and I ended up out here in the sunlight. And I don't know if I'm a better person in the end for having learned all this stuff.
Yeah, they say it's the journey, not the destination. So,
yeah, and the blueberries. All right, this has been Picture Me Coding with Eric Aker and Mike Mull. If you'd like to reach us, please send us an email, podcast@picturemecoding.com. Let us know. Have you heard of the CAP theorem? Do you believe that it is a popularly discussed topic? Why is it a popularly discussed topic? If you believe that it is, we would love to read and find out what people think about this.
Yeah, send us your thoughts on the CAP theorem, even if you think we're dumbasses.
That actually could be a useful bit of feedback if we really are pretty dumb. I'd like to find that out sooner rather than later.
Yeah, it's probably too late for me, but could help you.
There's still time for Eric to find that out and course correct. All right. Thanks so much, Mike. I will see you again next week.
See you next time.
Bye-bye.